Okay, so for our next part of our integration journey, we're looking at a particular application, and it links to some of the work on probability distribution functions and so on, with probability density functions in particular, and it's called the exponential probability distribution. So this is linked to what's hopefully prior learning for you, general continuous random variables, which hopefully you've studied to some degree before, and in particular the probability density function concept, in particular the normal distribution, which is symmetrical in shape. It has mu as its mean, and the standard deviation is sigma. Also, hopefully prior learning has included the cumulative distribution function, and you've studied probabilities associated with a continuous random variable. Okay, so let's introduce this idea of the probability density function known as the exponential probability distribution. And the skills, by the way, behind this are going to be calculus, integration in particular, limits, so integration and limits, and using technology to verify, especially graphics calculator. Not so much technology will be shown in this first video, however. And basically the function, the important function here, this can be written as f of t or sometimes f of x, is lambda e to the negative lambda t, where t is non-negative. Or very similarly, it can be written as f, just replacing the t of x really, and which is exactly what I've done there. That's x is non-negative. Okay, so lambda e to the negative lambda x, or lambda e to the negative lambda t. One of the big applications for this exponential probability distribution is often used to make or model the time between the occurrence of random events, because it's a random distribution. Okay, and then we can see the shape of the distribution. That can be t, because it's often time is the independent variable, but you'll see x as well. So it's just whatever symbols they use for the variables. So for lambda greater than 0, okay, the exponential random variable x with parameter lambda has a probability density in this piecemeal function here, and we basically state that f of x or f of t is non-negative. So just noting that last point, probability density functions are non-negative, so the function is non-negative. Because it's relating to probability, and the lowest value can be 0. 0 or greater. The area under the curve, total area, I should say area under the curve is equal to 1. Okay. Again, that should not be a surprise to you because you've got your prior learning. Now, symbols t or x, depending on which one you're using, that's the wait time for an event to occur. Okay, so it's the wait time for an event to occur in the distribution. Okay, and lambda, it's an average. Okay, so lambda is the average number of events in a time period. So depending on what the unit of time you're using, if it is to do with time, and often it is. So lambda is the average number of events in a given period based on whether it's x or t. And if it's t, it's time. So I'll just put time in quotes because it may not actually be time, but usually it is time period. Okay, and for example, that time period, as an example, might be per hour. Okay, not always, but. Now, using a bit of calculus, including integration and limits, we can show the earlier point that to be a valid probability density function, the area under the curve has to equal 1, and we can see that we've applied calculus there. So we start with the general expression. Because this is non-negative, it starts at 0 there. This is not something you'll necessarily need to do yourself, but this is where it comes from, using the limit. So see, as k approaches this upper limit of infinity, because we can't just substitute that in, we have to partially use limits. So once we take the integral, we then apply the limits, and it operates on that one there. Now that part there, for the rest of the video, I'll draw that bit out now. So negative e to the negative lambda x is negative 1 over e to the lambda x, okay, or k in this case, okay, and basically as k approaches infinity, we can see that this approaches negative 1 over infinity, which tends towards 0, okay? So that links to some earlier work you would have done on limits. Okay, so hopefully this example illustrates what we're talking about. So the time x minutes, again you could use t, the time x minutes that a shop assistant waits before the next customer arrives is known to be exponentially distributed for probability density function given by the expression there. So find the probability that he'll have to wait for more than 8 minutes for the next customer to arrive. So what we do is we're using our familiar probability notation. So probability that capital X, it'd be capital T if it was T, capital X is greater than 8. All right, so because it's 8 is the bottom, we don't have 0 at the bottom, we have 8. And as you know, the distribution goes on to infinity at its upper limit, and we put the given function, the active function, inside. So 0.2 e to the negative 0.2 x dx. Okay, now it's where we need to apply limits. So limit as k approaches infinity. And what that means is that that top limit, we have to apply limits when we're conceiving the the behavior and the tendency and the ultimate destination of that upper limit, because again we can't sub in infinity directly. So here we go, and that's applied, and let's do the integration now before we take limits. Okay, so whoops, didn't mean to put an equals. So square brackets, we've got negative e to the negative 0.2x from 8 up to k. Now k is going to approach infinity, but we're going to put k as a nominal variable there. That's unused so far. Then we evaluate the integral as much as we can, subbing those values in. So 0.2k minus negative, which is plus, and it'll be e to the negative 1.6, and that'll just come out as e to the negative 1.6 because I explained before what happens to the limit of this term here if you just scroll back a bit. And that's not a very meaningful answer, so a decimal approximation to 4 decimal places, 0.2019. Last part we're looking at is the mean and standard deviation of an exponential random variable. This is going to be sort of treated fairly quickly because you have assumed knowledge that you've come across things such as expected value, standard deviation and variance from your previous studies. So I won't be going through where those parts of the formulas come from. But if x is an exponentially distributed random variable with parameter lambda, we just outlining very briefly in this video how we find the expected value of x, and we use integration by parts, and within that we use limits, and I haven't shown that here. But that's the strategy that you would use, and it comes to 1 over lambda. Okay, and to find the standard deviation of x, we first need to find e of x squared. Okay, and then we use integration by parts again twice with limits in there. Again, it's not essential that you know this, but that is where it comes from. Now, from previous studies, variance is given by that formula from your previous studies, and hence we can get 1 over lambda squared. Standard deviation is the square root of the variance, so it comes out as 1 over lambda. Okay, that's where it comes from. It's not absolutely essential that you know that or be able to regurgitate that, but it's nice to know where things come from. Okay, so again, integration and limits developed that from our previous work. So the important thing is the expected value, which remember, expected value from your previous work is what we mean by the mean. Okay, and hence we have these two important results, so note those. Okay, finally, find the mean and standard deviation of the time that the shop assistant has to wait for a customer based on that information that we were using just a minute ago. All right, so the mean e of x is 1 on lambda. Okay, where that, remember, that's modeled as lambda e to the negative lambda x. All right, so lambda is 0.2, so it's 1 over 0.2, and it's in minutes. Okay, so that's 5 minutes. Standard deviation is the same. All right, so standard deviation is 1 over lambda, 5 minutes. Okay, so for an exponentially distributed random variable x with parameter lambda, we have 1 over lambda for the mean, and standard deviation is also 1 over lambda.